Great. I think that that's up and running. So I'll just briefly introduce. So first of all, thank you everybody for coming along to another INCOSE New Zealand meetup. Tonight we have Professor Anna Mijic from the Imperial College London, who has a really interesting topic in waters and in water and water systems and water system management that we're going to hear about today. So Anna, over to you.
Okay, so we're going to start again with the right one.
Looks good.
I mean, you can see that the title is very similar because what I do is systems approaches to water management, and what I was thinking, just showing you today, it's a bit of, I guess, motivation where this came from, and then the core part of the work we do, which is the integrated modeling of water systems with some examples of the work that has been published so far. And then I'm going to finish with a few things, what we are thinking about now and where this might go. And it would be great if we would have time for a few questions and discussion. So I guess the motivation for me and something that I guess I always start when I talk to anyone is that if we are thinking about the water as a system, we do it naturally. I always put this because I used to row, and there is a lot of memories, early memories for me related to water. But of course, then we move to something that is people much more familiar with the water, which is of course the infrastructure, but infrastructure both on the supply and the wastewater. And then we have different contexts. So most of my work is in the UK, although some of my work is in India. And then if you look at India, of course, this whole water context is very different. So we're thinking about water as a system. I guess we want to capture all the elements, which is the combination of the natural and infrastructure system, but also the human element in that system in different contexts. So what really inspired me and where the motivation for whole of the work comes is from a really nice book. So maybe people know about this. For me, I discovered it probably somewhere around 2016, 17, is a book by Professor Donella Meadows. It's called Thinking in Systems, and it's a great book that talks about a theory of systems thinking in environmental systems. And there are two things that I took out from that book, which somehow defined everything that I thought is missing in water systems. And so the first one is this notion of components, but then also links, so that we must understand not only one and two, but we must understand and for me this was a beautiful explanation of links. And then the second one, because I'm particularly interested in management, so I'm particularly interested in what do we do with water and how we make the best out of water systems for people, but also for the environment. This was the second one, which talks about imposing the will, which is exactly what we are trying to do. But because of that complexity, that imposing the will can become very challenging. And we have, of course, all the examples why water management is failing in so many locations. So the first thing we did with that, the first thing that I did with that was started thinking about, I call it the meta model, which is in my head the most abstract way of thinking about integration and water as a system. And that was inspired by the work. I was seconded to UK Environment Agency, it's an environmental regulator here in the UK, and they've just been published their 25-year environment plan. And in that document, there was a notion of the purpose of the plan to inform the good state of the water system, but the good state of the water system wasn't actually explicitly defined. And I started thinking, I mean, what do we mean by a good state of water system? And then one way of thinking about it is to say, well, ultimately, what we fundamentally care about is some measure of quality of life. And then if we think about that quality of life, and if we think about specifically about the water, one way of achieving the quality of life, and this is what we call, isn't it, reinforcing loop. One way of achieving quality of life is our dependence on the resources, in this case water resources, infrastructure that enables us interact with the environment, and then the same environment which provides the ecosystem services. So this is one way, of course, isn't it, of providing that quality of life through the infrastructure and the environment. And then we said, well, of course, what we also know is that there is a price of that. So when we extract our resources, we do create pollution, and that pollution will have a negative impact on the environment. But then we have also the third part of that, which I think is really important, which is what we call the development part, which is that the quality of life, of course, it's not only based on our reliance on the environment, it's a very much socioeconomic part, isn't it? It's the part where the resources directly support the development, and then the development supports quality of life. And we played with this meta model, and what we did with this is to define these loops. So we call this first one, the socioeconomic one, we call it resources dependence loop. What we call this big one, it's environmental capacity. So it's how much we can extract from our environment without damaging it. And then we have the last one, which is infrastructure management, because our environmental capacity, of course, will depend on the way how we design our infrastructure. And the whole hypothesis, which we published in this paper 2 years ago, is that unless all three loops are considered, we are going to fail in some shape or form. And we used what is called socio-hydrological phenomena, so known paradoxes of unintended consequences of water management, and we managed to map them, 6 of them. We managed to map them on the same meta model, and for us that was theoretically something that gave us evidence that we can think about this way, that we should think about this way. And if then you project this to anything else related to systems and water, it actually works. And this is what Donella Meadows talks about, isn't it? It's the leverage points. The biggest change in the system is the change how you think about the system. And I think this was at least our attempt to get people to think about system in a water system in a different way. So I'm just going to give one example from that work, which is, again, also something that people very easily remember. And this is one of these paradoxes that we discuss in the paper. It's irrigation efficiency paradox. Is the paradox where actually applies to any technology development. So we see that very often with other technologies. In this case, it was the example of introducing the water efficiency, the irrigation efficiency, and irrigation efficiency, of course, uses less water for same or even increased yield. So, and you can see the color coding. So this was, again, this is technological solution on the infrastructure side, and we see the pink part be the development part getting triggered, which is of course good. We want that because we know that it improves the quality of life. In this case, definitely it increases the productivity and profitability of farmers. But of course, there are processes that function only in the development of resource dependence loop, which is what was observed then, that before farmers have increased their yield with less water, what happened, and because it wasn't regulated, is that farmers expanded their land. And of course, if you expand your land, it is logical what will happen next is, because even if you use less water, if you have more land, you will, in the end, or if possible in the end, that you increase the water use and possibly increase the water use even beyond what was initially there before the efficiency has been introduced. And of course, this is the environmental capacity bit that wasn't considered, and it wasn't controlled. And there are a couple of examples again in the paper, and for me this is really interesting to think a bit about the change. This was the management change, but then thinking about the potential implications and trying to predict unintended effects and regulate them. In this case, of course, the solution would be to regulate allowed agricultural land expansion. So we started there, and then of course we wanted to translate all of this to quantitative scale, and most of my work at that time was really here. So very detailed process modeling with relative local scale, or we also did something around this one. Global statistical modeling, looking at this meta model at the global scale through the indicators. But for real decisions or for understanding the water system in the complexity of that integration, we thought there is something missing here. And we were fortunate to get large UK government funding in 2019, which enabled us to create a team and start developing integrated modeling. And we call the model WSIMOD. It has different pronunciations. What the thinking behind the model is that we now wanted to have a look at all the components of the water cycle. And if you want to represent the water cycle, integrated water cycle is probably the easiest way to do it in a centralized manner. So we have our hydrology, we have our land, the groundwater, it goes into the river, we take the water out, we use the water, there is a runoff, the water goes to the wastewater and goes back into the river. So this is the easiest, maybe more simple way of representing the integrated water cycle. We said, well, this is what physically is connected at operation. This is what we want to model. And what it was also important for me is that in this representation we had all the elements of the water of our meta model. So we thought it is probably the most reduced complexity representation of the integrated water system. And then when we started, of course, looking at this is how do we do this? What was important for us is to capture the physical part and the human part. What was also important for us is to capture the physical processes so that we can do the interventions, so that the model has physical meaning and that we can infer the parameters and input from the data, but that it also has, of course, the human component, isn't it, of the cycle. So when we started looking into the literature, one of the options we had, and if there are people on the call who do water system modeling, they would recognize some of these models. Basically, each of these components can be modeled and is modeled using different types of detailed models. So if you want to do hydrology, you can use something like SWOT. If you want to do groundwater, people use ModFlow. Rivers, HECRAS, Spyware is a tool that's used in the UK for water resources optimization. If you do any networks, lots of people use EPANET or SWIMS for water supply or wastewater. So each of these, there were options for each of these components. And of course, these are just some of the examples. So one alternative we had is to go into what is called in the theory integral modeling. So to take these, and this is now very simplified representation of a model, to say, well, each of these is an integral model, isn't it? So say this is SWOT, this is ModFlow. And what we could have done is to say, well, let's take the models and let's try to couple them externally. Of course, I mean, there are techniques you can do that. You can do different types of external wrappers. Open MI is one of those. But we have also, I mean, we knew technically it wouldn't be easy, but we also found this beautiful paper from Voinov and Schugart. It's an old paper, it's 2013. He talks about what they call integronosters, and they talk about the challenges of adding these models, which are developed separately together, and they give these 4 key reasons, which were all something we wanted to avoid. They're difficult to understand in a sense because they are very often coming from very different modeling theories. They're hard to validate because they have different parameters that are defined in different ways. They're computationally always very, very intensive, and their modularity is almost non-existent, because once you change one, the whole link might change. So we thought, well, there must be an alternative, and this is really the acknowledgement of the great work of Dr. Barney Dobson, who was a postdoc on that project. So Barney looked at the literature and said, well, why don't we try a hybrid approach? And we call that compositional modeling, where instead of taking different models, we basically find the reduced complexity representations that fit our representation best. We recode them, enabling direct links between the components. So this is all now one software where we explicitly add the components. But we also, instead of having the wrapping, we develop internal bespoke orchestration that, rather than having the internal solver, governs the sequential movement of the pollution and the water, the flow and pollutant within the system. So this has to be defined, but what this gives us, the computational efficiency, because we don't have a numerical solver, high modularity, because we can change and we can connect any link with any other link, and in this case, these nodes are the representation of different components. So behind each of these nodes is a model, and then these links here can have different characteristics. So they could be simple propagation, or they could have rules within them, as well as the rules here, which enable us to represent any management decisions. So human behaviors, which we wanted from the beginning. It is easier to understand because everything is within the same modeling framework. I would say it's possible to validate because the model is completely integrated. So if we move one part of the model and change, everything else is changes. So we can at least track the uncertainty and attempt to validate the system as a whole. And as I mentioned, is highly modular, and we were really happy with that. So how the model looks like. So this is if you look at the catchment, which is our basic spatial unit where we can close the water pollution balance. This is the representation. So what we did, if people are familiar with the conceptual type of modeling, they would represent this usually the natural part of the system, so land, groundwater, river. What we did, we added other parts of the system in the same representation with explicit, again, representation of the use, and then very flexible representation of these links. This is the QR code should take you to the paper that leads directly to GitHub. So the source code of the model is completely open and available for anyone to use with a pretty good documentation. And then what we get from the model is, for a catchment as a kind of minimal spatial unit, we get time series of flow and different water quality indicators. And we normally model nutrients. So this is suspended solids, nitrogen and phosphorus. We could model other pollutants, but depends on the data we have. And our default spatial temporal resolution is daily. So we usually do daily time step. And of course, we do the validation. And we normally validate the model on the flow and water quality in the river, because this is what we have the data for. Although we can validate it on other parts. And we do have examples of the work where we also validated the groundwater representation. We are doing now validation around the wastewater effluent. We can validate on the supply reservoirs as well. So of course, soil moisture, ET. So we can validate on different, and this is really interesting, of course, because it does show a lot of potential for equifinality in these complex models. But of course, it is an interesting thing to examine. I have to mention two people explicitly. I mentioned Dr. Barney Dobson, who is behind the framework and who coded the urban part of the code. And we were very lucky to have a brilliant PhD student together. Dr. Liang Liu. Liang coded the rural part of the system in the core WSIMOD representation. Of course, the whole team and since basically 2018, most of PhD students and postdocs have and are working on some aspects of WSIMOD. So for the rest of the talk, maybe 15, 20 minutes, and hopefully we'll have time for some questions. I'll just show some of the examples of the work. What is really good and what we are very happy about is that the model works relatively well with minimal calibration. And these are just some of the papers that we publish, different versions of the model. We call the model now WSIMOD, but in the early versions of the work we did, again, we developed the urban representation and then the rural. So there are models that we call CityWatt and CatchWatt before we got WSIMOD. But these are the 4 key case studies we published so far. And you can see they cover different aspects of England, from North London, so River Lee, Upper Thames, Norfolk, and then our big study in Manchester, which are very hydrologically different in water management context. And in all of the, and you can see that the sizes of the catchments and of the regional systems are very different. Upper Thames is our biggest model. You can see here that on average, and this is the performance for the flow in different catchments, we use normally what is called a Nash-Hartley efficiency, and you can see here that anything above 0.5 or 0.6 is really acceptable. You can see the performance, of course, in some better than the others. And then this is the performance for the nitrate. We sometimes use percentage bias, sometimes Gupta efficiency, where generally kg around 1 or percentage bias around plus minus 20%. And you can see that normally all the water quality is very difficult to validate. We are doing relatively well. Why we say the minimal calibration, and this is something that we are working on now, we don't do automatic calibration because you've seen the model. It's very difficult for us to understand exactly where the problems are coming from. We do manual calibration because of we know which some of the components which are more sensitive, which is especially on the land node side. And we know that normally when we are not performing that well is that some information in the system is missing. This is normally around water resources side because these data are not publicly available. And then the other aspect we know we are sometimes struggling to capture is the inflows into actually the wastewater and the effluent part of the river flow, or in the complex groundwater setups, because the model is conceptual. Sometimes that can be an issue. So rather than calibrating the model, what we are trying to do is to find more information, and this is our ongoing work. We have set up now the model anywhere in England and Wales at water frame directed resolution, so that is more than 4,500 catchments. And we are starting with a fully uncalibrated model. So these models are all manually calibrated for different case studies. What we are doing at the moment is setting up the model and testing how we can improve the performance of the model without the automatic calibration, really understanding what information we are missing and which processes we are missing, rather than trying to fine-tune the parameters. Why we like the model and how we use the model. I like to call this to be a detective work, because if you have integrated models, then you can really ask the model different questions. This is one of the works we did with Young after he finished his PhD. We looked, so this is the Upper Lee case study. This is the River Lee. Thames is here. This is north of London and the hinterland. It's a big groundwater system, and one of the things that is really interesting here is that lots of obstructions come from this region. And one of the water management options that UK Environment Agency is considering is reduction of abstraction licenses to increase the low flows in the river because of the ecological constraints. One of the things we did here is to say, well, if what we can do if we know where the abstractions are, we can reduce the abstractions equally, or maybe we can use the model and try to track where the water is coming from. So this is what we show here. So if this is, for example, the location, which is really important for the environmental flow, so this is something where we want to ensure that there is enough water. What we can say is, well, let's see where the water is come in this location, where's the contribution of different catchments to the flow in this river, because if we know where the highest contribution is, maybe this is the catchment where we should reduce the obstructions most to let the water come back to the river. And this is what we call the assessment point. And what we can do with the model is to develop these profiles of the flow. And you can see here, this is standard base flow separation, but the base flow separation also shows not only what is the percentage of base flow, but where the base flow is coming from and at what percentage. I think the other thing which is just interesting here is to understand that here more than 50%, for example, in this system, the flow is actually coming from other inflows, and that other is either surface runoff or the effluent, which is very important for human impacted systems. So what we did with this information, we said, well, why don't we then do, of course, different abstraction scenarios? So this is the default, something that the Environment Agency was considering, which is the equal ratio reduction. So we equally reduce the abstractions from all the catchments that currently have the obstructions, and we look at the change in the obstruction. So this is how less water we are taking out, and then we are looking at the implications for the mean base flow. So how much more water will be in the river if we do this? And this is again the default. And then we do two scenarios. So we do what's called the prioritized reduction, so reduction in those catchments that contribute most. And then we do one more, which we call prioritized and adjacent. So we look at also the proximity of the catchment to the assessment point. And we see that in both scenarios, so if we compare this, we either have the same amount of base flow, so new water in the river, with much less reduction in the obstruction, so more water for the resources. Or if we have the same amount of reduction, which is of course not good news for water companies, at least we have more water into the river. So both of these options, at least theoretically, would give better options and better results for both the water company and the Environment Agency, other than the basic option to equally reduce water obstructions. We also can use the model to develop options that originate from integration. And this is one of our earliest work, and we haven't actually explored this, I think, in a level that we could now. But the thinking behind this is very simple. So if this is our integrated system, what we know is that in the rivers where we have the discharges and supplies from the same river, which is at least in England the case for about 60% of the rivers, we can take this information and try to understand what is happening and try to see if this integration between the abstractions and discharges can actually give us an option. Of course, one problem that we have, a big problem in England, is this problem of untreated spills. So water coming from the wastewater without treatment and creating the pollution in the river. So what we did here is to look at the integrated system and to plot different relationships. So in this case, we look at the precipitation and the percentage of the untreated effluent. And we look at here the same information, so percentage of untreated effluent, so this is this blue arrow, and the supply reservoir volume. And why this is important is because, so if you see here, so all the red dots is where the precipitation is higher than 10 millimeters, so all the days when the precipitation is higher than 10 millimeters, which is likely to trigger spills. And then we also see for the same days in the supply side is these are all the days where the reservoir is basically full. Okay, so what that triggered the thinking is to say, well, why don't we use this information and say, on those days where we have the rainfall, when we have the high rainfall, why don't we minimize abstractions? So reduce the abstractions. We introduced the rule that reservoirs has to be more than 99% full. And what will that have? What will physically happen is that because we are minimizing abstractions, we're leaving more water in the river. If you have more water in the river for the same pollution, you will improve the water quality. So you will dilute the pollution and theoretically improve the water quality. So we did that, and we look at the results, and the results were really nice. So we call this abstraction effluent dilution option. And we look at the phosphorus without the option and phosphorus with the option. And you can see here, especially for these high concentrations, this is 101. This is what would happen if isn't it you do nothing. You see the reduction in these high concentrations, which we then calculated would be if you would if we want to do the same with the storage, it would be equivalent. We would need to build around 180 megaliter volume storage, which of course is a huge investment. And then if we check what is happening in the reservoirs, of course, here we want the line to be the same because we don't want to affect too much the supply side. And of course, there are almost none of the negative effects. I think there's only 6 additional days in the 100-year simulation period where the supply comes in the lowest level of restrictions. Because we have the integrated system, we can also look at the co-benefits and trade-offs. So when we think about the management, what we do with the management, we can change any of component, or we can change or add any of the links. And this is also when we talked about the beginning about thinking, different thinking. For me, thinking about water management is thinking about functional relationship, which is to say, well, if I want to increase my supply, I can add storage, or I can reduce leakage, or I can reduce use, or I can redirect water, or I can increase the storage in the land. So rather than saying nature-based solution, I think about it as a functionally what will happen with the water in the system. And this is also, again, our early work, but one way to look at that is then to say, well, what are different options that can happen across the water system? And we see few supply side, few wastewater side options, some of the green options, green roofs, rainwater harvesting. And then we can look, and this is what we always do, we look at the performance across different metrics. And it's really important to look at how the options change all the elements of the water system. And you can see here what is really nice and what we kind of expect, but it's not very often quantified, is how the supply side options have lots of co-benefits on the wastewater side, which of course is expectable because the system is physically connected. Demand reduction, really significant positive impact. So the more green means that the results improve compared to the baseline. Reservoir, of course, mainly or only on the supply side. This is our new option on the abstraction dilution, which really has positive impacts on the wastewater side. Of course, the wastewater options less benefits on the supply side. Of course, rainwater harvesting shows here. But I guess what is also really interesting is that we have sometimes, isn't it, we have this pink, which means that the option is worse than the original. And this is the wastewater reuse, where we say, well, why don't we take some of the wastewater and put it back into our supply? if we do the wastewater reuse, what is happening? And you've seen in the previous slide that effluent can be a big part of the river flow. And if that happens and we redirect part of the water that's actually relatively clean, we reduce the downstream potential of water to dilute pollutants. And there could be a negative, depending on where the scheme is and what is happening, of course, downstream. But this is definitely something that needs to be checked if the wastewater reuse scheme is introduced. And then my final example is the work that we did where we looked with the link between the housing and water management. And this is something which I think is really important because at least in the UK, housing and development come first, and then water goes second, trying to accommodate all the new development. What we wanted to show with this work is what is the price of that, and we did the case study of this is the old London plan. New is coming out any day now. Around 500,000 homes in London by 2030. And what we did is added those houses in the model, and then we simulated the impact. And we look particularly at three indicators: increase in the demand, increase in the surface runoff, and increase in the pollution in the river. And what we did is to say, well, what is the impact? So these are these dashed lines. And can we introduce a range of measures, in this case, completely on the housing side, to offset that impact? And if we can offset the impact, which we can, I mean, numbers here show, we call it water neutrality. So what we can we achieve water neutral London? Basically having the London with the indicators, which are the same before the development was introduced. Of course, it doesn't mean that these are good indicators. It just means they're not getting worse. And we managed to do that in the model. Of course, what is the difficult part is what needs to be implemented. So to achieve the water neutral London, the model said that all the new houses would need to have efficient appliances, 80% of the green roof, introduce demand reduction and greywater harvesting, and that wasn't enough. So we had to start retrofitting, and we had to retrofit almost the same amount of homes with efficient appliances and greywater harvesting, and we had to introduce almost 20 square kilometers of the new green space to get to these numbers. So theoretically, the model says it's possible. In reality, would it ever be implemented? Probably not. And I think this is the message that we always try to communicate. What is the price of the development in cities, and especially in the very densely populated cities as London. So I'm gonna finish with this, which is what next and what we are doing now. Of course, because the model is very flexible. We are thinking about the new functionalities. One thing that I'm really interested in, we did start thinking about this, but we want to explore this much more, is the control systems, to look at the optimization and control and really maximize the value of the model, because we can represent different decision rules. One thing that is, of course, very interesting is water transfers and wastewater recycling. So we're going to start looking into that. Most of our, as I mentioned, applications is in UK, which is a very centralized system. We will be expanding the model in other case studies, looking at specifically this decentralized water management. We are starting a big project looking at the water system in Paris, and they're particularly interested in decentralized options. We are thinking about technological representations. Again, we can simulate a lot of nature-based solutions. Is there anything on the innovation and technologies which we can try to represent in the model, or even that the model can inspire some technological innovations? And this is the kind of purely the kind of modeling aspect. So we are doing lots of what we call the nested or hybrid modeling. One of the ways to do the nested modeling is to replace some of the components with detailed models. So we are now replacing, for example, the groundwater part with ModFlow. Why? Because one of the questions that water companies and environment agencies is asking is, say, well, if you do these abstraction licenses changes at the catchment scale in an aggregated way, what are the implications for different river reaches? And we cannot see this with our model, but if we nest mod flow, so if we just replace the groundwater component with little model, we can start looking into this. We are, of course, experimenting with the AI. So we're starting looking especially the LSTM models, and specifically for the water quality. There's also very interesting, the model actually performs really well, even with very limited water quality data. Observations in the UK are pretty bad. They are monthly on average samples, but even with that information, LSTM is overperforming WSIMOD by far. We are looking into that. And then this is the last bit, which is quite interesting. And this is part of this big project we've just started. So it's Schmidt Sciences Philanthropy Foundation. They designed what is called the VIEW program, which will focus on development of global water reanalysis data. And ours is one of the 4 projects which will be looking into that. And our purpose specifically is to look at the local knowledge and the new information that we can add to the models, either on the input side or the validation side, which will likely need to have some form of LLM agents or some form of AI simulation to be able to upscale. So this has just started. The team, we are assembling the team, and the program is 5 years. So hopefully there should be some really interesting results coming from this work. And this is all from me. Thank you so much, and I would be very happy to answer any questions.
That was awesome, Anna. Thank you very much for that. I think we've got plenty of time for questions. I've got my eye on the participants list, so feel free to just come off of mute and throw one in. I might start though with a question about. So one of the last things that you talked about was some of the complexities around regulation and human behavior, and the effect that has on the effect, how those might get incorporated into a model in the future. I wonder if you might, so you talked about Paris and other urban environments. Are you interested in doing that kind of analysis on other different sort of areas? What comes to mind is within the United States, for example, or the states in Australia, neighboring municipalities may have radically different, and if not diametrically opposed, policies around what water quality looks like, what requirements are for water quality. I wonder if you have looked at, if you've identified any places where those kinds of regulations, where they're so different, but still governing or still influencing water quality in the same body of water, that's an inelegant way of asking a question. Are you looking at the influences of things like regulatory frameworks?
Yeah, I think I understand what you mean. I mean, it's we can, so the basic spatial unit is a catchment, but because the model is intended to look at the interactions, so we usually model large regional systems, which meaning tens and hundreds of catchments again. So the one that we currently have is for all of England and Wales, which is almost, as I mentioned, more than 4,500 catchments. So you can then, select the area where you have specifically, if your main question is the implication of different regulatory or policies, you can specifically select the region, implement the policies, and see the implications, and then do the what if scenarios. So we do, when we have the information, I mentioned that especially in UK, water resources is not open. I mean, we can have information about the consented obstructions, but we don't have the information about operational rules. because there's a security issue. But when we do have that information, we do add all of these rules. We can add one of the things how we check the water quality is looking at the water quality in the UK is regulated by the Water Framework Directive. So we can look not only the water quality by absolute value. Sorry, there is a beauties of working from home. There is also we do check water quality based on the categories around the Water Framework Directive, so good, bad, and so on. So we can look at different ways, isn't it? Either implementing the regulation or post-processing the results so that it basically checks if there are different, for example, criteria in different states. We can check them differently and see what are the implications. And I would also say, I think the model, if anything, is really a policy model, a bit more than because I mean one challenge we have is because the model is aggregated at the catchment scale, and you've seen, I mean, most models are actually quite detailed models. And then the question we normally have from, say, organizations that are so used to working with detailed models, because they can't see the detail, they don't trust the model. And then what we are trying to emphasize is that the model will see the interdependencies rather than details, but that you need to understand the interdependencies before you go into the details. That is our mantra. Sometimes it works, sometimes it doesn't, but it is a model that is mainly intended almost as an additional layer to detailed models to scan the system, look at the interdependencies, see almost like the boundary conditions of the kind of different planning and I guess specifically options, because what we can look at is which is happening in reality, what if everyone implements whatever they want, what happens? And that is not done normally together, and of course then you cannot anticipate some of the changes that happen if you don't simulate them together.
Great, thank you. Dunish has asked a question in the chat. From your experience working with water companies and environmental regulators, what's the biggest practical hurdle to getting these disparate bodies to adopt a shared systems-based baseline?
I mean, this is so. I didn't have a slide here. I have somewhere a slide of my pet project, which is to try to get to the UK government and persuade them exactly to do that. And it's very difficult. I think one of the reasons is, again, the trust. It's a new model, it's a new way of modeling, and we did some projects with especially with the Environment Agency, and they are kind of getting used to what they're seeing from the model. They haven't actually used it yet. But I must say that at least from the UK example, our biggest supporters were actually the city. So London and Manchester, they both have what they call so they're Greater London and Greater Manchester. So they are city authorities which oversee many boroughs, and they see themselves because they have to look at the kind of the whole of London, whole of Manchester. They are actually being most proactive in a way of really trying to understand and look at the evidence from the whole system, because they don't make decisions themselves, but they work with lots of stakeholders, and whatever other organizations make decisions they make directly impact what is happening in the city, and they're responsible for the functioning of the city. So they had the incentive to look at that. So we did big project in Manchester and big project in London, but that, I mean, when I say that we did the modeling, we did, there was a bit of engagement and so on. It hasn't been used yet. So I'm not sure what is when and how it's going to be used. One thing that is also happening in England is that the UK government has published the new guidelines for the change of policy in water regulation, and they propose something which is called the regional water planning as a new way of planning. So currently we have water resources planning, wastewater planning, and there's environmental regulation. They want to integrate it a bit with that regional water planning, but we don't know yet what exactly that is going to be. I think very often from the practical perspective, because they see systems approach as the way that people need to collaborate, which is completely true. And then the collaboration is much easier at a local scale. So what they do in collaboration, they collaborate around individual projects, which is of course great. I think it's still very difficult for them to kind of collaborate around the large scale decisions, maybe because much bigger decisions would need to be agreed and with many more financial implications.
New Zealand had an initiative that was started to be stood up and then was stood down at the change of the last government, called the initiative called Three Waters, where instead of having small sort of regional or even municipal authorities over, governing wastewater, freshwater, stormwater, that was it was intended to be a more centralized, holistic approach, but was clearly it didn't end up happening that way. So maybe some interesting modeling like this would help. But there's another question in the chat here. What can we do to support your work? The audience here is largely Australia, New Zealand. How can we, obviously we'll share your presentation to us. But what could we do in Australia and in New Zealand to support you and the modeling that you're doing as it relates to water systems?
What would be really great is that we try to do WSIMOD New Zealand and Australia. I mean, the project that I mentioned at the very end. So the project just started, and the idea is to, and you said you've seen that it says WSIMOD anywhere. So because the whole program is about developing global water reanalysis data set, which is kind of interesting. So it's equivalent, if people know about the climate reanalysis, so it's equivalent of that just for water. I'm just looking at the chat. Yes, yeah, some acronym. So they will be. So what we want to do with WSIMOD in the next year or so is to try to develop a setup, at least the baseline setup from global data sets, which basically means that we can just say, let's try what is happening in Australia, and we can set it up automatically, even if it's not the best model, that there is some model. Because what we've realized is that it's easier to start with a model, run some initial validation and see what we need to change and improve, rather than trying to get all the data and then kind of delaying the model setup. So that will be happening within a year or so, that there will be at least an opportunity, and we'll at least have some list of global data sets that we will be pre-processing to set up the model anywhere. But if there are specific case studies, and I think what we found most easier as a collaboration, if they are like PhD students or MSc students that are interested in this kind of work, that they can, because the code is so if you go to GitHub and you download the code, you can just try to set it up yourselves. There's pretty good instructions. So Barney did a really good work in documenting. We are always very happy to collaborate. And if there is an MSc student or PhD student who are technically good, so good in data processing, good in Python. The model is written in Python. I should have mentioned that. They can probably set up the model in a couple of months, at least the initial baseline model, which maybe won't be perfect, but it will be running model. And then I think the question is, what is interesting from your perspective? What are the questions you want to ask from the model? So what are these other policy or planning or integration scenarios that you might want to, use the model for, which will then define the case study, the details, and so on.
Can I just ask a follow-up question? Thank you. So just to break it down for my simple brain. So in the UK, you've got those other models that are already collecting data, and you are taking that data and then breaking it down to make a new model from all those different data sets. So, for example, in Australia, we'd need to know the equivalent of those things. Are they the same ones? Are they different? Like, I'm not in water, so like how difficult is it, I guess? Are they similar models that you're starting with, or are they completely different that we'd need to deconstruct?
The models we have already selected the modeling representation, so that's all coded in. So you don't have to code anything. I mean, unless you want to change something in the model. What you need to do is to get the data that go into the model. And in the UK, I mean, I can send the list of the data set we use for the model setup. And I believe specifically in Australia and New Zealand, I mean, you probably have all of those data
Very
publicly
similar.
available.
Yeah,
Yeah.
sources.
So
Okay,
which
cool.
are the kind of normal, I mean, the hydrological data, they are there. What is, of course, always more challenging is the data on the urban side, on the water resources side. But again, even there, we can make lots of, approximations. So we would need to know where the wastewater plants are, where the discharges are, where the obstructions are, where the reservoirs are, some information about the networks, percentage of leakage, combined separate system, and so on. So some initial ideas about the kind of pathways and so on, almost like a perceptual model of the system. But then, data collection and pre-processing, we have, again, algorithms that can do that. And that's a nice exercise for the students. I think what is maybe also important to mention is that the model can handle different spatial scales. So we mentioned that we are by default modeling at the catchment scale, which is how we aggregate hydrology, but the water resources information is at the water resources scale, and the wastewater is at the wastewater scale. We just overlap and align inputs and outputs so that we normally, but we can simulate. We do simulate all the components of the system. So we can look, we have a PhD student now who is specifically looking at the wastewater effluent. And of course, what we see is that the wastewater effluent, which is not really well, because we have now the data available. We managed to get the data for the wastewater effluent in the UK. The wastewater effluent looks very much as a river flow. It's very dynamic, which we shouldn't expect from the wastewater, but we do. So lots of inflows other than wastewater. But then we also have, of course, the situations where we don't get the good wastewater validation, but we get the good validation in a downstream river. So we are getting maybe the river flow good for quite wrong reasons, which I think is really, really important. So we are trying to go now into these internal fluxes and to see that we try to get the right result for the right reason, which is, I think, very difficult, but I think crucial for integration.
And sorry, final one, and then I'll go on to the other question. So do you currently have any existing relationships with universities or anything in ANZ at all? Just for our context, if it's something we did want to look at.
So there's a colleague who used to work with me. She's in the University of Sydney, but she is completely on the systems integration project. So very different background. I know some people, and I can probably dig out the names. I know Professor Anna Deletic. Anna is, I think, in Melbourne, if I'm not sure. But we haven't worked with either Australia and New Zealand. I guess for us it's quite difficult because unless they're bilateral, isn't it, agreement, there are not many opportunities. So if you have any colleagues or any contacts, that would be great. Yeah.
Horizon Europe is a great excuse potentially for us all to work together on stuff like this, especially now that Australia is an associated country, like New Zealand is. So for things along those lines. Did you have another question, Beth?
That's it. I'm going back on mute, but thank you very much.
One more question here in the chat then from Jen. How can hydraulic models, asset condition data, and growth demand forecasts be effectively integrated into a single consistent systems framework to improve the reliability of capacity planning decisions across the Three Waters network?
I mean, this is a super interesting question. So it can be, so what we do with the urban networks is that we represent them at the aggregated scale, okay? So which is a huge approximation. But what we need to do, we need to move the water, isn't it, through the system, and get some of the physical behavior, okay? I mean, it's an aggregated model, so it has loads of simplifications. So, and this comes to the point, what do you want to use the model for? So if you want to look at the model from the perspective of urban networks, you wouldn't use it. If you want to use the model to say how my, what will happen in my city if I kind of change my supply and my wastewater side, then you can look at that. I can send the links to some papers. We did two things here. So demand by default is very simple, but you can add a much more complicated or complex demand generator. So we did that in one of the papers. We looked at the impact of COVID on water in London. So, and because we wanted to look at the changes of working from home, we took out that simple demand and put in the demand generator, which takes into account the commute. And then in COVID, of course, we switched off commute. So we let people stay at home. And of course, then you kind of use and discharge water in different catchment than if you go to work. And actually the model was sensitive to that. And the other thing we did with the wastewater side, we've shown that, so you can nest the model. So if you really want to know what is happening in a detailed network, and keep the boundary conditions with the integrated model, you can just take out the simple representation and, for example, nest swim. We haven't published that, but we did do the trial, and it can work the same way as we do, for example, with mod flow now for the groundwater. Or you can try something which we published actually, which is to develop these kind of reduced complexity networks. So what we did, we took we use InfoWorks, but it's same as Swim, and we did a bit of network simplification to basically come up with some less detailed model than InfoWorks, but more detailed model that is representation in WSIMOD. So you basically get to still some spatial representation, but it's still computationally much more efficient than the full detailed model, which is very slow, isn't it? So that we can run continuous scenarios, and that actually worked quite well. So there are different, I think, kind of techniques to get more detail into the integrated model, but I would say for different subsystems. So I wouldn't go detailed everywhere, but you kind of zoom in where you want to look at. And then even if you zoom in, you can zoom in to different resolutions, depending on, again, of the question that you want to ask the model.
Beautiful.
Did the thing. Thank you very much. I think we're probably out of time for today. Really appreciate you coming and presenting to us. It's always cool to see, well, any presentation that starts with a screenshot of, the canonical systems thinking book is going to be a good one. So thank you for coming and speaking with us, for sharing your research. And who knows, maybe we'll find an excuse collectively to work together in the future. And to our audience, thank you for your attention. Thank you for attending, and look forward to seeing you at the next one. Cheers, everybody.
Thank you so much. Bye-bye.
Thank you.